Swayam Prabha. Digital India. Educated India.
Hello everyone. So this week we are going to study about the boundary layer theory. This is the week 4 of hydraulic engineering course. So we are going to go straight to the slides now. So when a real fluid flows past a solid, the fluid particles stick to the solid surface. So that is one of the phenomena that happens, and the velocity of the fluid particles close to the solid boundary is actually equal to the velocity of the boundary, and this phenomenon is called the no slip boundary condition. For a stationary body, the fluid velocity at the boundary is going to be 0, because as we said in this point above, that the velocity of the fluid particles close to the solid boundary is equal to the velocity of the boundary. So if the boundary is stationary, then the fluid velocity at the boundary is going to be 0. So actually this is the most commonly used no slip boundary condition that we use in a viscous fluid flow. What is viscous fluid flow? A small detail which we have already talked about before, but we will look into more details in the upcoming lectures in coming weeks. So what happens is, far away from the boundary, the velocity of the fluid is actually higher, and the velocity increases from 0 value on the stationary surface to free stream of the velocity, free stream velocity of the fluid in the direction normal to the boundary. So if this is the case, that happens when the surface is stationary. If it is moving, then the velocity at the boundary is going to be the velocity of the surface that it is on. So because of this phenomenon, what happens is, there is a velocity variation, and this gives a velocity gradient du by dy, which exists in normal direction. So in case of, say for example, this is the boundary, because of no slip, and this is stationary, and suppose there has been a velocity coming in. So we are not going to talk about let us say in between right now, but we say, suppose here is the velocity u, right, and this distance is y, and of course because this is stationary, at this point the velocity is going to be 0. So the velocity gradient to be du by dy. Okay. This velocity variation occurs in a very thin region of flow near the solid surface. So far away from the solid boundary, the velocity is going to be the velocity with which the flow was actually coming. So this whole phenomenon occurs in a very thin region, and this layer, this thin region, is called the boundary layer. This is the diagram which has been adapted from S.K. Som book of fluid mechanics, Introduction to Fluid Mechanics and Fluid Machines. So what happens is, if there is a flow that has, suppose, the velocity u that is coming, and there is a flat plate of length L here, what happens is, when it encounters, there starts developing a thin region. So I will show you the, so this is a thin region, and above this this thin region the velocity will remain u, but below that the velocity will start varying. It goes from 0 at this point to, say for example, u at this point, and this is the existence of the velocity gradient. This is where the velocity gradient is going to exist. I am not saying it is going to be constant du dy, but there exists a non-zero velocity gradient, and this thickness we are going to talk about it later. This is at any distance, this is the boundary layer thickness. So, Prandtl actually divided the flow of the fluid in the neighborhood of the solid boundary into two regions to have a more simplified look. So, one is called the boundary layer. Okay. So, it is in the immediate vicinity of the solid boundary where the viscous forces and rotationality cannot be ignored. So, there are two things that cannot be ignored in the boundary layer, the viscous forces and the phenomenon of rotationality. We have seen in the previous lectures that most of the flow in the water is considered irrotational. We are going to explore that into more detail when we study the viscous fluid flow. So, as I said, in the boundary layer these are the things that cannot be ignored, and in this region there will be a velocity gradient equal to du by dy, and therefore the fluid will exert a shear stress tau on the wall, which we assume to be equal to mu du by dy, where mu is the eddy viscosity. Then the second region is called the outer flow region. The velocity is constant here and is equal to the free stream velocity. As I told you in the initial slides, that above this boundary layer the velocity will not be affected. It will be the same as the free stream velocity, that was the velocity, the flow was coming with whatever velocity it had before, the same will be maintained above this boundary layer. So, all the phenomenon that is happening is in this boundary layer. Boundary layer is a very important phenomenon actually in oceans or rivers. All the phenomenon such as the sediment transport or the transport of phytoplanktons larvae it occurs in this particular region, that is called the boundary layer. However, above that, that is the outer flow region and the velocity remains unaffected. So, in this there is no viscous forces that we consider and the flow is essentially irrotational, and therefore the potential flow techniques may be utilized to obtain the velocity field. So, we have talked about potential flow in the previous slide, where we in the previous lecture where we studied about the streamlines and the potential flow in a topic called fluid kinematics. So, this figure has been taken from Sengel. The name of the book is Fluid Mechanics Fundamentals and Application from McGraw-Hill Higher Education. Here it shows that the flow is coming with a velocity v, and there is a plate here. You see, this is the plate, and if the flow will pass over it, this region that is enclosing the flat plate is actually boundary layer as indicated here, and the flow here is rotational as we have seen, and with some finite viscous forces. So, viscous forces will exist in this region, and the region outside is outer flow, where the flow is inviscid or there is no viscosity or friction, and we can consider irrotational region of the flow here. Now, after this brief introduction, we will talk about how the boundary layer grows over a flat plate. This is the most simplified object that we think of is the flat plate. Above, when the flow will pass over it, how the boundary layer will grow above that. So, to do that, we have to consider the flow of the fluid having free stream velocity u, and that happens over a smooth flat stationary plate placed parallel to the direction of the free stream. So, something like this. Okay. So, I will explain the terminology here. This is the velocity, the free stream velocity where the flow is coming, this is the velocity u, and it encounters a plate here. So, this is the plate. I will take away the ink now, and because the flow will strike the plate here first, that is called the leading edge, and this is point A. So, after that we will come to see why this is laminar zone, why this is transition zone, why this is turbulent zone, but just to show you the in the diagram. So, the first few units over the flat plate is going to be laminar, that is the laminar zone, after which the flow in this region is going to be a transitional zone, and after that this is a turbulent zone where the entire flow will become turbulent. So, now we have put the drawing here, so that will be of help when we start writing some of the equations. So, as I told you before, the velocity of the fluid on the plate surface is 0 because of no slip condition, as the plate is stationary. But at some distance away from the plate, the fluid is having certain velocity, that velocity we do not know for now, but at some distance away, suppose this distance for example, that is away from the plate by this much, it will have certain velocity. Therefore, because of existence of this velocity, a velocity gradient is set up. This is x direction, let us say this is y direction, and this velocity gradients results into shear stress, because for existence of shear stress is proportional to du by dy, the rate of change of velocity with the distance normal to the flow. Okay. Now, the presence of this shear stress, what it does is it retards the fluid motion in the vicinity of the plate. So, this the existence of the velocity gradient will induce shear stress, and that is going to slow down the fluid motion near the plate, and the boundary region therefore will start occurring at the leading edge, because that is the first point where the velocity is 0, and as soon as we go over and above it, there will be certain velocity. So, that is the first point. Before that, any point will have the velocity u. The boundary layer grows with the downstream distance from the leading edge x. So, this is the direction x. So, as soon as we start moving in the x direction, the boundary layer will keep on growing in thickness. So, let us say this is delta, that is the boundary layer thickness at any distance x. Okay. So, one of the important parameters that you have read in the fluid flow is Reynolds number. So, there is going to be a Reynolds number associated with this type of phenomenon, that is the occurrence of or the development of the boundary layer, which is given by, as given here, R e at a distance x is given by u x by nu, where u is the free stream velocity, here x is the distance from the plate, a leading edge, and nu is the kinematic viscosity of. of fluid. Okay. Now, what is laminar boundary layer? We are going to continue. This is the laminar zone, right? So, we are going to concentrate on that. Near the leading edge of the plate, the flow in the boundary layer is laminar. This is important to note. And the length of the plate from the leading edge to the point up to which laminar boundary layer exists is called laminar zone. So, this is the leading edge here, right? So, the length of the plate from the leading edge to the point where the laminar boundary layer. So, here the laminar boundary layer is existing until this point as indicated in this diagram. So, this distance is called the laminar zone. This one here. So, for a flat plate, it has been found out that the laminar boundary layer occurs up to Reynolds number of 5 into 10 to the power 5. A lot of people have done research, experimental results confirmed by numerical analysis, and this value has come up. So, if the Reynolds number is less than 5 into 10 to the power 5 for a flow over a plate, the laminar boundary layer will occur up to that particular point. And then there is a turbulent boundary layer here, a little bit information on that. Actually, with increasing x, as we have seen, Reynolds number as x increases, as we saw that Reynolds number as a function of x was u x by nu, and x is in this direction. So, as you keep on moving in this direction, x is going to increase, and therefore, the Reynolds number will increase, right. Now, when the Reynolds number increases to more than 5 into 10 to the power 5, the laminar boundary layer becomes unstable. Unstable means the velocity will have some fluctuations. And then there is a transition from laminar to turbulent boundary layer. So, this is the transitional zone here. So, this short length over which the laminar boundary layer changes to turbulent is called the transition zone, indicated by this distance here. Okay. Now, the downstream of the transition zone, the boundary layer becomes turbulent because x keeps on increasing and therefore, Reynolds number increases, leading to fully turbulent region. Now, as you see in this diagram, there is something called laminar sublayer. Okay, and what is that laminar sublayer? This is a region where the turbulent boundary layer zone, and it is very close to the solid boundary. Okay. So, basically it is a region in the turbulent boundary layer zone. So, this does not happen here, but it happens in the turbulent boundary layer, and it occurs very close to the solid boundary. And here, because viscosity will play an important role, therefore, the viscous effects are dominant, they are much more than the other type of forces. Since the thickness of this layer, as we can see, this is very small compared to this, right, the variation of the velocity can be assumed to be linear. Okay. So, in laminar sublayer velocity profile is assumed linear. Linear with respect to what? With the distance, increasing distance linear. That means with increasing y. Well, okay. And we also assume that this has a constant velocity gradient. So, the velocity gradient du by dy is constant. Okay. Therefore, for linear variation of velocity, we can write du by dy is equal to u by y. Okay. Now, the shear stress in this layer is constant and is equal to the boundary shear stress given by tau naught, as we have already been using naught for the tau naught for the shear stress near the wall. This is also, it is like a sort of a wall only, this is the boundary, and therefore, we can write tau naught is equal to mu du dy at y is equal to 0. Or using this equation we can write mu u by y. Now, we will talk about another phenomenon, that is distortion of a fluid particle within a boundary layer. What happens? So, this figure has been taken from Monsoon, Young and Okishi's Fundamentals of Fluid Mechanics, published by Willy and Sons. So, let me just, so what it says is that the fluid particle retains its original shape in the uniform flow outside the boundary layer. That is very true, because outside the boundary layer there are no effects, and the fluid particle, this is the fluid particle above the boundary layer, this is the fluid particle that is going to be in the boundary layer. So, when it moves in this direction, there is no problem at all, because all the points will have equal velocities, right. However, this particle here, after entering the boundary layer, the particles begin to distort, as you can see. This is, but this starts distorting, and when it goes, it distorts more, right, depending upon what the velocity gradient, but there is definitely is a distortion from this point to this point as soon as it enters the boundary layer. So, why this distortion occurs? This distortion occurs due to the velocity gradient inside the boundary layer. How? Because the top of the particle has a larger velocity than its bottom. So, this point here, the bottom, will have lesser velocity than at the top, right, because this is more closer to the solid surface, the lower part, the surface which is closer to the solid surface here. Therefore, the flow inside the boundary layer has a non-zero vorticity, because what does vorticity causes? It causes rotation, right, and this is what we see, the fluid particle will rotate, and this happens because of the differential velocity at the top and at the bottom surface. And what we can see is, in the turbulent boundary layer, the particle becomes greatly distorted. So, in the boundary layer, the flow is rotational. Okay. Now we are going to see what the boundary layer thickness is. In real sense, physically, there is no sharp edge to the boundary layer. Okay. Now the boundary layer thickness is the distance from the plate at which the fluid velocity is within some arbitrary value of the free stream velocity. So this is an important term, boundary layer thickness delta. We have seen similar term in some slides before. And what is this boundary layer thickness? It is distance from the plate, the flat plate over which we have considered the flow. So distance from the plate at which the fluid velocity is within some arbitrary value of the free stream velocity. Ideally, at the top of this boundary layer, the velocity should be equal to the free stream velocity. Normally at the top, so this is the boundary layer. So because of this is the velocity is going to be 0, and at one point we have to consider where the boundary layer ends. So we assume when the velocity reaches almost 99% of free stream velocity, the boundary layer ceases to exist above that, and that thickness is called the boundary layer thickness. So what is so special about 0.99? Why not 0.96 or 0.98? To remove this confusion, we will now look at some of the definitions. Some of the definitions is displacement thickness given by delta star. Very important term in this particular module of hydraulic engineering. There is another thing called momentum thickness, that is called theta. Okay. And then there is something called energy thickness, which is given by delta double star. Okay. So these three are in boundary layer analysis. So we consider two velocity profiles for flow past a flat plate. So this is flat plate here. Okay. This is section. This is the one velocity profile, this is 2, and both has equal areas. Okay. And this figure has been taken from Monson, Young and Okishi, Fundamentals of Fluid Mechanics. So as you can see, okay, I will explain these terms as it comes. So this is a uniform profile. Okay, where mu is 0, so there is no viscosity, and there is going to be slip at the wall, this place. Okay, it's not, I mean here there will be no slip condition. Okay. The second is the boundary layer profile. This is the uniform profile, and this is okay, this is the boundary layer profile. Here there will be some viscosity and mu is not equal to 0, and there is going to be no slip at the wall. No slip at the wall means the fluid velocity just above the plate is going to have the same velocity as the plate. In this case, since the plate is stationary, the fluid particle just above this will have a 0 velocity. So, that is why the velocity profile you see it is 0 here. In profile, in the uniform profile, at the beginning there exists some, the u is here, okay, there is a uniform velocity u, it is not 0. So, within the boundary layer there is a velocity deficit, okay. So, this is the boundary layer. So, u capital U is the uniform velocity profile, here also the free stream velocity is same, but say at this distance if the velocity is u, right, then the deficit of the velocity that is happening is u capital U minus small u. Small u here is the velocity at a point in the boundary layer. So, this is the velocity deficit equal to. Because of this deficit, the flow rate across the section BB. So, this is the section BB. I am going to remove, sorry. So, because of this deficit, the flow rate across the section BB is less than the flow rate across section AA. That is correct, because the velocity here is limited, I mean less than this u by small u, okay. So, the velocity in the boundary layer is lesser than the uniform velocity profile by u capital U minus small u. Suppose what happens if the plate, my question to you is what happens if the plate is displaced at section AA by an amount delta dash. So, here this delta dash is called the displacement thickness, okay. With this we will see in the upcoming lecture, okay. So, the question at which we are going to end this lecture today is that what happens if the plate is displaced at a section AA by an amount delta dash. So, this is enough for today, and we are going to start the next lecture by answering this question. Thank you so much, see you in the next lecture.